I was gonna say,
Probably not.
what happened to it?
No.
I just got to put my while I did that. This is like, these are like the highest ones on my
You guys ready for the weekend?
The guy who won that one? The guy who won nationals last year.
I know this is the highlight of the what you've been waiting for. Hope you're all putting in the paperwork to change to the math major, right? What? Math majors, future math majors, yes?
No.
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 Crushing my strings by theory. All right, I will begin with a word of prayer. As it is now. Dearly Father, we thank you for this day. I thank you for these students. And I pray you with us, help us to glorify you what we do and just understand a little more about math together. Lord. In your name I pray, Lord Jesus. Amen.
So I need to try to get your attention about something, which is that factoring a polynomial is not solving p of x equals to 0. These are related, but these are different. If I ask you to factor a polynomial, your answer should not be 2 and 3. Your answer should be like an expression with x in it, right? If I ask you to solve the polynomial equation, then the answer should be like, you know, a number or a couple numbers, a statement that there are no numbers which solve the equation, right? This is how it goes. So be more explicit here. Example 1. Pretty simple example. Here it is. X squared minus 100 equals to 0.
This is an equation. I could ask you to solve it, right?
And so we could solve this by going, you know, x minus x plus 10, right? Times x minus 10 equals to 0. Lo and behold, x equals to minus 10 or x equals to 10. So this, what I just did here, is solving x squared minus 100 equals to 0, right? I solved it. I found the numbers that when you plug in, it works, right? And then those are all the numbers that make it work, right? That's the thing about solving. It's not enough just to find a solution. We insist you find all the solutions, right? That's the understanding. Or it's also understood, and this is kind of an annoying thing, but it is the way we mean it. If we say solve it and there's no solution, you say no solution, well that is how you solved it. Which is kind of a funny thing to think about it, right? Saying no solution is a solution. Anyway. Example 2, on the other hand, if we have p of x equals to x squared minus 100, well, and maybe I should have done this first, but oh well. This is factoring. Factoring is not solving. These are different. They're related, sure, but they're different. So if on the next quiz or test or something, I say factor these polynomials, and you solve them instead of factoring them, it makes me sad. It makes me very sad. So you don't want to make me sad. Don't do that. Then I have to take your points away. I don't want to do that. I've got enough points. Don't give me more. Right? So this right here is p of x factored completely over the real numbers. All right? Now there's a theorem called the factor theorem, which relates the factors to the solutions, right? Like every linear factor gives you a solution and vice versa. We'll learn more about that later. I'm not saying these problems aren't related. They're deeply related, but they are nevertheless distinct questions. Yeah? Okay, so hey, let's look at another example. Example 3. And by the way, I should probably mention the critical identity for today is, again, a squared minus b squared is a plus b times a minus b. This right here is your difference of squares formula. You want to make sure you know this and looking for ways to use it. We just used it here, didn't we? Because I thought of 100 actually as what? I thought of 100 as 10 squared. 100 is 10 squared, right? Let's do one that's a little bit harder. Example 3. What if we had like, and by the way, like right up until the end of the class, rest of everything I'm going to be doing, the question every example is paired with is factor this polynomial. I'm not going to write it 10 times, but every time I write a polynomial up there, the instructions are factor the polynomial, all right? So I'm not even going to talk about solving anymore today. We talked more about that last class, so let's focus on factoring this time. Completely. Okay, so what if I had something like p of x equal to, oh, I don't know, 9x squared minus 31. That's kind of annoying. Can you factor that? No? Let me restate that. You can factor this. How should you do it? I'll do the easy part. You got yourself a 3x quantity squared. That's what 9x squared is, right? That's a square. How do I write minus 31 as a square? Square root of 31 squared, we have a winner. Yeah, that's the ticket. Now you got the pattern. You've got a squared minus b squared, and we're back to the difference of squares formula again. So here it is. It ain't pretty, but you know what? It's factored. Game over. End of story. We got it right there. Right? Any questions so far? You might wonder, what if we have a plus instead of a minus? Let's try that on for size. So example 4, what if we're up against something like, you know, p of x equals to, let's do the easiest possible one, x squared plus 1. See, it doesn't seem like we can factor that, right? And it doesn't look like a difference of squares, does it? But there's something we can do to make it a difference of squares. And this is a kind of sneaky step, so watch me. We have an imaginary number, right? The imaginary number I has what? It has I squared equals to minus 1. That's the definition of the imaginary unit, right? So what does that mean about 1? 1 is equal to what then? See this? Minus I squared is equal to 1, right? So with that sneaky trick, this is x squared minus I squared. So guess what? Difference of squares. Again, always difference of squares. And so, here we go. X plus I times x minus I. So this makes p of x factored over a complex number system. So that C letter there, that's the set of complex numbers. Do you guys know what complex numbers are? I don't know if I've talked about it too much. C is equal to like, you know, a plus bi, such that a and b are real numbers, and I squared is minus 1. That's the complex number system in a nutshell. If you watch that video I sent you a link to, you can learn learn lots about the history of complex numbers if you're interested. But anyway, this polynomial factors over the complex numbers, right? But this polynomial does not factor over the real numbers. Do you see that? Well, here's a theorem of advanced mathematics. The factorization, if it exists, is unique. In our context, it's unique. So if there's a complex factoring, there cannot be a real factoring. In other words, it is impossible to rewrite x squared plus 1 as a product of two linear factors. You cannot reduce it. So this kind of polynomial, something like this, is an example of something that's called irreducible. Irreducible, or some books will call it a prime polynomial with respect to the real numbers, or I could say over the real number system. So the universe of numbers that you're allowed to use to set up the factoring matters. If you've got complex numbers at your disposal, everything factors. All right? On the other hand, if you've got real numbers, some quadratics factor and some don't. There's really just three ways that a quadratic can factor. And we'll see all three of those ways today. I've shown you two of them already. The one way that a quadratic can factor is it can factor into distinct linear factors like this. See this? Distinct linear factors. Real factors like this, like that. The other way that could happen is it doesn't factor over the reals, so it's prime, like this, all right? What's the third case?
Doesn't factor?
Can't be factored.
We'll discover it soon enough.
Complex anything.
Let me do one more example like this before I go on. We'll come back to my third case in a second here, but example 5, what if you're up against, oh, I don't know, p of x equal to x squared plus 17? How would you, if you wanted to factor that, first of all, we should all agree, prime over the reals. All right, it's prime over the reals. If you've got a sum, like a x squared plus a number, and that number is positive, you can't factor over the reals, all right? If we're allowed to use complex numbers, though, we can do like this. This is x squared minus I times the square root of 17 squared. Try it out. If we take I root 17 and we square it, what happens? Yeah, we get I squared times the square root of 17 squared, which is also known as minus 17. So I've got, see, I put this minus in here to be fair, because I had plus 17, so to make this into that, I have to put a minus. Let me erase some of this. I knew one of these has like a really bad sprayer, so see if the other one isn't totally stupid. Maybe it's not. Yay! Right. All right. So then, finishing blows, right? We just do x plus I root 17, parentheses, x minus I root 17. That's factored over the complex numbers. Now, if the instructions on this problem were factor this polynomial over the real numbers, I would probably have a parenthetical if possible, if not, write prime. This is the one where I would say you should write prime. This is a prime polynomial over the reals. Again, over the complex numbers, we can always factor, right? So, like on the next test, I usually have one problem where I say factor these polynomials over the reals, and then I've got like 10 of them. All right, so they're like all just factoring over the reals. And then I'll have like a token problem somewhere where I've got like maybe three quadratics, and I say factor over the complex number system. So I usually only ask you to factor over the complex number system over like one problem where you're just looking at quadratics, and the lion's share of the other examples we just focus on the real polynomials. All right? But it's important to be able to recognize when the quadratic that you're up against, you cannot factor it no matter what you do to it, all right? So we need to be able to recognize those. Because if I just pull one out of my hat, you know, like this, oh, I don't know, p of x equals to x squared, you know, plus, oh, I don't know, 12x, plus, let's say, 37. Factor it if possible. Is it possible to factor that? We don't have to guess. All right, there's a method. Let me show you the method. I showed it to you last time. I'm going to show it to you again. What do? We complete the square. So we take half of this. I should circle the 12, right? What's half of 12? 6. So we take x plus 6, square that, subtract this thing we added here, which is 36 in this case. And then that right there, what I wrote in red, is identically equal to the x squared plus 12x. If you FOIL it out, you'll see you get a plus 36 and a minus 36. They cancel. It just leaves you with the x squared plus 12x, right? Now that 37, it's still there, like so, all right? And then what happens? Well, you're left with x plus 6 quantity squared plus 1. Done. If we're factoring over the real numbers, at this point, it becomes manifestly clear this cannot be factored over the real numbers. This means prime over the reals. How do I know that? Well, I can factor it, right? How does it factor?
Take the I times the square root of 1?
Yeah, we changed the 1 to
Oh,
minus
right,
I squared.
right. Negative I squared.
Yeah, so we got x plus 6 plus I, x plus 6 minus I. So there's the how it factors over
Forgot 1 doesn't exactly.
over the complex numbers, right? So if the factoring necessarily involves complex numbers, it is a prime polynomial. It's irreducible. Now, you don't have to factor it over the complex numbers in the problem that I said just factor over the reals. You just stop once you complete the square and you get plus a number. You're like, oh, okay, done. Can't be factored. All right? What happens, though, if in example 7, say I have p of x equals to x squared plus 12x plus 30. Well, again, completing the square, I get x plus 6 quantity squared minus 36 plus 30, right? So these two terms are the same as those two terms. They're identically equal. That's completing the square. Half of the x component, half the coefficient of the x added to x squared, subtract the square. Then what happens? Ooh, look at this. See, this is different, right? X plus 6 squared minus 6. Very different pattern, right? We complete the square, we got a minus.
So we should do what? We should take 6 and write it as the square root of 6 squared, so we can use our difference of squares formula, right? How do you write 6 as the square root of 6 squared? Well, here, I'll use a different color to add contrast, but you just do this. Watch. Oops, very silly, but there it is. You can do that. Like, how old are you? 18? So you get the square root of 18 squared all. See how it works? Take anybody's age, square it, take the square root, that's how old they are, you know? Or you can take the square root of their age first and then square it, that's how old they are. Go either way. Yeah?
What's the point of doing that?
Oh, because then it's that pattern. That's the point. Is it now it fits the pattern, difference of squares, which means I can factor it. X plus 6 plus the square root of 6. X plus 6, that's a good question. Like I said, it's all about the difference of squares. Completing the square makes the problem become that much closer to difference of squares. All right?
So we just have to fit the pattern no matter what.
Well, what I'm showing you is that we can always manipulate a quadratic polynomial to become a difference of squares pattern. That's not true in general. Like if I tried to show this for a cubic equation, it's not nice. There's like special tricks for the cubic equation. Like there's a special thing you can do to eliminate the squared terms from the cubic. If you have just like an x cubed and x, it becomes what's called a depressed cubic. Those things are beyond college algebra. We don't teach those, and no one should. All right. I mean, like for some reason, my wife learned these things in high school. I don't know why, but she learned like the cubic formula and the quartic formula in her high school. They're like the cubic formula is like a half a page long. The quartic formula is like a stone cold page long. You won't find them in your algebra book, right? It's beyond your authors. The author probably doesn't know them. I mean, I'm just joking. They better know. But for a quadratic though, the strategy I'm showing you today is ironclad. Always works. So let's try another one. Now I have been deliberately avoiding. Odd numbers for coefficients of x, right? So let's face the music there, see what happens. Oh man, did I answer your question? I don't know if I answered your question now.
Yeah.
Yes. What was the third? I guess I should probably go back to the third case, right? Let's try one. How about this? We've got example 8. P of x equals to x squared minus 6x plus 9. Let's complete the square on this thing. So I take x plus what? Or minus what? What do? I got a minus 6 here, so I do minus 3, minus half. Half of whatever is here goes here. What is the square of minus 3? It's 9, so I have to subtract 9. Of course, we've still got the plus 9 up there, right? So this is identically equal to that. The 9s, they be canceling. What happened? X minus 3 squared. This is the third case, a repeated factor. So when you complete the square, there are 3 things that can happen. When you complete the square, you can either get your square and then minus a number, you can get the square plus a number, or you can get the square and the number cancels out and gives you 0. Those are the 3 cases. When you get minus a number, then we can do the real factoring like we've done. When you get plus a number, you can convert it to an I squared and then get the complex factoring. But those are the three cases. We've already seen them. And by the way, you're like, that's dumb. I don't need to complete the square here. I already know how to do this one. How many of you feel like that for this one? I hope you do. Because this is what? This is just factoring, right? It's just plain old happy day, right? You just, oh, well, 3 times 3 is 9, so I just put a minus 3 and a minus 3 here, right? Right?
Yeah.
You knew that. But notice what completing the square has done. First, imagine yourself so tired. Oh, that's a bad thing. Imagine that you somehow forgot how to factor. We have derived it. It's an algorithm. You take half of that, you add it, you subtract the square. There's no guessing. It's just a machine. You are now a machine, right? Who will not give me any points on the factoring quadratics. They will not get you, right? Yeah.
Where'd the -9 come from?
That's completing the square. So the answer is, if I square this x minus 3 squared out, that, when we work it out, is x squared minus 6x plus 9, right? So if I'm originally having these x squared minus 6 terms, I can replace, see there's an identity here, x squared minus 6x is equal to x minus 3 squared minus 9. So what I'm doing is I'm taking this x minus 6x, x squared minus 6x term originally, and I'm trading it for an equivalent expression, namely x minus 3 squared minus 9. They're identically equal. This is that. Because the 9's cancel. So that's where the -9 came from. The -9 came from the fact that once I add this square, I'm effectively adding 9. So to be fair, I must take it away. And it just is a coincidence here that this is also 9. That's just a quirk of this example, right? All right, but I made it seem simpler than it is, right? I'm trying to sell you something. So let me show you what happens. There are fractions. It can happen. It's true. There are fractions. So let's try one with fractions. How about this? Step 9 could be something like, x squared plus, I don't know, 3x. And I'm gonna do one that we can do with factoring just to show you how it works. But we already know this is gonna work out nice, right? You guys can factor this without completing the square, right? How does this factor? You guys already know what's gonna happen, right? X plus 2, x plus 1, or x plus 1, x plus 2. Which one comes first? The x plus 1 or the x plus 2? What's that? It doesn't matter? Very good. It doesn't matter, that's right. But the 1 comes first. Because I wrote it that way. Sorry, I'm an idiot. So let's complete the square on this, just to see how it gets to that. This would be x plus, what's half of 3? Well, 3 halves, right? We square that. Now we have to subtract the square of what we've added, which is what? 3 halves. What's 3 halves squared? 9 fourths, right. So I subtract 9 fourths, and of course I've still got the plus 2. Again, just to emphasize, these two terms are these two terms. They're identically equal. That's the completing the square step. What is, can you add fractions? What is 9 fourths? What is minus 9 fourths plus 2 equal to? Minus 9 fourths plus 2 is minus 9 plus 8 over 4.
5 fourths.
I believe we have minus 1/4, right? Because 2 is 8 quarters, right? So if you have 8 quarters minus 9 quarters, leaves you with minus 1/4. So this is actually equal to
x plus 3/2 squared minus 1/4. But what do? Can we factor? Yes, we can factor, because after we completed the square, we got minus a number. So we can factor over the reals. Okay? So we do our usual trick. This is the square root squared, right? What is the square root of 1/4? I heard 1 second. You are correct, because it's 1 over the square root of 4, which is 1 over 2. Or you could use your calculator, whatever. So what we got? We've got ourselves x plus 3/2 minus 1/2 squared. Right? Which is parentheses x plus 3/2 plus 1/2, parentheses x plus 3/2 minus 1/2. Using the difference of squares formula again. What is 3/2 plus 1/2? 4/2. What's 4/2?
2.
2. So we've got x plus 2. What's 3/2 minus 1/2? Well, it's 1. So we got x plus 1, and, well, of course, right? Not question. I know once you have a hammer, everything looks like a nail, right? That's what completing the square is, it's a hammer. Should you use it? For this problem, absolutely not. This is totally the wrong way to do this. What was the right way to factor this? Right at the top, right? So if you can see how to factor using your previous course's method, right, or like I did at the start of all this, then do that. By all means, do it. But if you get stuck, what do? Complete the square, right? We can take any of these apart, right? Let's do another one. Now there's something I haven't dealt with yet, which is how do we deal with when we've got like a coefficient in front of the x squared? How do we deal with that? How do we deal with that? Say cry? What? No. Give up. Cry yourself to sleep. Cry yourself to sleep? No. Please don't. You should just remember that we covered it in this video and come back here and rewatch what I'm about to do. That would be my advice. Okay, so example 10. What if we're up against the dreaded p of x equals to, oh, I don't know, 3x squared plus 2x plus 1. You want to factor that. All right? Or maybe it can't be factored over the reals. We'll find out, right? I want to make sure this will factor. So instead of putting that plus 1, let me be a little bit annoying and trade that out for a minus 10. I'm pretty sure if I put a minus 10 there, it's going to factor. Let's see how. So listen, we've already seen a bunch of examples with completing the square, right? I've showed you guys like about 10 times now, right? But I have never showed you yet when we have a number in front of the x squared. So how do you deal with that? Pull the 3 outside, right? So that's 3 times what? 3 times x squared. That's easy enough. But if I put a 3 out here, I had a 2 before, what do I have to do? Plus what? Plus 2/3 x, that's how we factor 3 out. Right? If there's no 3, we just create a 3, right? Because 3 over 3 is 1. So you multiply that back out, 3 times 2/3 is 2. We're back where we started, right? The ultimate judge of factoring is when you unfactor it, when you multiply it, does it work, right? Okay, so minus 10 what? Minus 10 over 3. Now if you doubt me, distribute. Multiply the 3 through. Does it work?
Yes, it works, right? 3x squared, 3 times 2/3 is 2x. 3 times minus 10/3 is minus 10. We can always do this trick. Anytime you have a coefficient of a, which is not a coefficient of the x squared, which is not 1, you can just factor it out. We're talking about factoring right now, right? We don't have the option of just dividing by 3. I can't just divide by 3. I'm not talking about setting this equal to 0. I'm talking about factoring it. So I can't just magically make the 3 disappear. All I can do is just pull it out and keep it out in the front and let it sit there as we do our thing. All right? If we were solving t of x equals to 0, well then you could divide by 3 and make it go away. All right? But that's a different problem. Now what? Equals to 3 times what? We've got ourselves an x. What's 1/2 of 2/3?
1/6.
1/2 of 2/3. Try that again.
1/3.
Yeah, the 2's cancel, right? We get 1/3. So x plus 1/3.
2/6.
Yeah, 2/6 also. But we'd like to write 1/3 because 2/6 is like more writing, and we don't like to write. So x plus 1/3 squared. We're completing the square. What do I have to do? I now have to subtract the square of the thing I added to x. So I subtract this. I subtract 1/3 squared, right? Which is 1/9. Right? 1/3 squared. 1/3 times 1/3 is what? 1/9, right? Now what's still there? 10/3 is still there. We can't ignore it. It's biding its time. Waiting to be added to the other term. All right? So this, again, is that. We're just completing the square. Then what? We should add fractions, right? What's 1/9 plus 10/3?
So that's 31. So 1/9 plus 39.
1/9 plus 10/3, also known as 1/9 plus 30/9, right? Multiply these by 3/3. So you got yourself a 31/9. How about this 3? It's still out there. It's like it's stuck outside the party. We're never going to let it in. It's like that roommate you have. You don't tell her that you don't tell them where you're going. You know, you'd be annoying. Let's see here. No, I'm sure you don't have a roommate like that. Let's see, 31. I probably was that roommate. 31/9. What's that there? Okay, great. All I did was arithmetic. That stuff, add the fractions. You have a calculator, you can do it there, right? And then we'll do what we always do, square root of square, right? Square root of square. So I take the square root of this, square it. Lo and behold. Well, let's simplify that a little bit more. What's the square root of 31/9 equal to? Well, it's equal to the square root of 31 over the square root of 9, which is the square root of 31/3. Right, so I'll write it down, one more step. 3x plus 1/3 squared minus square root of 31 divided by 3, quantity squared. Now, the thing in the square brackets is our favorite thing. It is the difference of squares. So yet again, we will use a plus b times a minus b. Right? And so the pattern, here it is. So we've got x plus 1/3 plus the square root of 31/3, x plus 1/3 minus the square root of 31/3. And there you go. There you go.
Any questions? I didn't start with this because this is kind of scary, right? I have been careful to show you examples of completing the square where the numbers were nice, they were even. So when you divide it by 2, you still had a whole number, and then it makes everything seem so much easier, right? As soon as fractions enter the chat, you guys all want to leave, right? Like it's like fractions are so annoying. But we can deal with them just like this. Any questions? So at this point, you're like, well, this is lovely, but we've been doing all these examples with, you know, numbers, and I really would like it if you would instead do an example that has letters for coefficients instead of numbers, right?
Well, I don't think it.
I hear what you're saying, so yes, I'll do it. You're enthusiastic about this. Good. So let's do it with letters. Let's see how this goes. Now that we understand the method. By the way, what I'm about to do, actually, you can take as the algorithm. All right, this is the template on how to do any of these problems. So what I'm going to do, I've showed you the steps as they play out on example after example after example. I now am just going to do the steps on an arbitrary example. The same set of steps though. All right, here it goes. So we'll begin with p of x equal to ax squared plus bx plus c. So it begins. Then we do what? A is non-zero. Factor it out. Factor out the a. We've got x squared plus b over a times x plus c over a. Let me make it a square bracket to make it just like my example 10 looks. All right, so that was like my factor the 3 out step. I just factored a out. Then what's next? What's next? Well, next we are going to complete the square. But now we've got letters, but that's fine. What is b over, what's b over a over 2? What's 1/2 of b over a? It's x plus b over 2a. So it's just that. We square it. We have to subtract the square of that. So minus b over 2a, quantity squared. And then we've got this plus c over a term over there, right? It's riding along, minding its own business. There it is. Again, I'm just completing the square. Again, just the completing the square stuff. But here is the completing the square stuff in general, I guess, in ugly letters, but there it is. Now what? Now I just do a little bit of formatting here. So let's say a, x plus b over 2a, quantity squared, and then minus, and I'm going to rewrite this. If I want to have the same denominator, I like this 2a squared. I'm kind of liking it a lot. So I could rewrite this as b squared minus 4ac all divided by 2a quantity squared. All right, the denominator is already a square, so happy day. We don't need to do anything to that. The numerator, on the other hand, is not yet a square, so what do we do to it? We do our, I'll write it one more line. So we got a times parentheses x plus b over 2a, quantity squared minus, well, the square root of b squared minus 4ac divided by 2a, quantity squared. Guess what? Difference of squares, right? So then we can factor it, right?
I know what that is.
You know what it is? I feel like I'm up to something, huh? Let's see here, x plus b over 2a plus the square root of b squared minus 4ac divided by 2a, parentheses, x plus b over 2a minus the square root of b squared minus 4ac over 2a.
Okay.
Yeah,
Where did you get the 4 and the numerator?
I made a common denominator. It was a sneaky step. So look here, I've got a b squared over 2a, b, let me write it here. So we had this plus c over a, right? So that's b squared over 4a squared plus c over a. So there's a minus on the first term, right? And so that's what I had here. Are you with me? So to make a common denominator, what do I do?
You have to multiply both sides by the same thing.
Right.
And top and bottom.
Exactly. So what am I missing? What am I missing here to get from here to here? I'm missing a 4a, right? So that's what went on there. I'm just multiplying.
Should have had to multiply both.
So that's how I got from here to there. But notice that there's a minus out front. So I kept the minus out, which is what changed that that plus to a minus to factor the minus out. That algebra step was very Machiavellian. I did medieval all at once. You studied your political. Anyway, okay, so we factored it. The beauty of this calculation, though, is we can appreciate the 3 cases. What are the 3 cases? Case 1, right? B squared minus 4ac greater than 0. That says distinct real factors, right? If we have, on the other hand, case 2, b squared minus 4ac equals to 0, then we have a repeated factor. Do you see that? Appreciate what I'm saying? If b squared minus 4ac is 0, this term is gone, that term is gone, and we're just left with x plus b over 2a in both places. So it's just x plus b over 2a squared. That's the repeated case. What's the other possibility? The other possibility, case 3, we could have b squared minus 4ac less than 0. And that would correspond to the prime case, or irreducible. Do you guys remember what this thing is called? Did anybody ever tell you? This quantity under the radical, this b squared minus 4ac, what's it called? Anybody know? So b squared minus 4ac, this is the so-called discriminant. And the reason it's called the discriminant is it discriminates what kind of quadratic you have, whether you've got one that factors with the reals, or it's repeated, or it's complex. So one thing you can do whenever you're up against a quadratic, when you want to decide whether it factors or not, you can just take the coefficients a, b, c, stick them into the formula, b squared minus 4ac. If it works out to be positive, wonderful, you can factor. If it works out to be 0, you're looking at repeated. And if it works out to be negative, then you've got a prime polynomial on your hands. Of course, we can discover all of those things by completing the square. Now, some of you were saying, that looks familiar, what's going on here? If we set this equal to 0, what do we get? What happens if we set this equal to 0? So, in other words, ax squared plus bx plus c equals to 0 implies x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. That's what you get from setting those factors equal to 0. This is a derivation of the so-called quadratic formula. My larger point to you here is that by completing the square, you're building the quadratic formula for your factoring each time. And it's actually not hard. All right, I have a quiz to give back to you guys.